Okay, Theorem 19, the circle theorem, it says in a circle, an angle standing at the center, so this angle AOB, will always be twice as big as the angle at the circumference ACB. So what are we given here? Circle K, just K is what we call it, doesn't matter what you call it, with a center at O. Points A, B, and C stand on the circle. The angle AOB is at the center, and when you're drawing this out yourself, the first thing you do is mark the center, then draw the circle. So you need to know where the center is, so have it marked. Then the angle ACB is at the circumference. Both stand on this arc AB, which I've marked a little bit darker. I'm not sure how clear it is, but that's from here to here is the arc AB. We want to prove that this angle AOB, the size of that angle is twice as big as the size of this smaller angle ACB. And just to demonstrate what we're doing here, I've taken this triangle, if I fold it in half, I get an angle that's half the size of that original angle, and that fits perfectly in up here. Okay, so we're just trying to prove that mathematically. How do we go about doing that? Well, our construction is we want to join C to O. Okay, and then extend that line out to some point. It doesn't matter quite where you put that, but we'll call that point D. And what we'll notice that we've done here is we've made O to C is a radius, so is O to A, and so is O to B. Okay, so straight away we can say, well, in our proof we can say the triangle AOC, this one here, is isosceles. Excuse me, the second part of our construction, label our angles. Okay, so I'm going to call this angle at O, I'm going to call this 1. I'm going to rename that, I'll call that O up there. Call this one 2, 3, 4, 5, 6. But of course, because we know that AOC is an isosceles triangle, we can say 3 and 5 are the same. Therefore, the angle 3 is the same size as the angle 5. We can also say triangle OCB is isosceles, and therefore the angle 4 is the same size as the angle 6. Okay, where do we go next? Well, we're going to say this angle 1 is actually the same as 3 and 5 together. That comes from theorem 6. If you remember that one, that this external angle is equal to the sum of these two internal angles, if I call them P and Q. And that applies even if you've got, a funny shape here. If that's my external angle, it's still equal to the opposite interior angles added together, P and Q added together. So we can say that the size of that angle 1 is the same as 3 plus 5 together. Okay, which is just 2 multiplied by 5. Okay, because remember 3 and 5 are the same size. Same thing, we can say the size of this angle 2 is equal to 4 and 6 together. The size of 4 plus the size of 6 together, which is 2 times the size of the angle 4. So, when I finish this off here, 1 plus 2 together, the size of the angle 1 plus the angle 2 is equal to 2 times the size of 5 plus 2 times the size of 4. Well, that's 2 times the size of 5 plus 4 together. Okay, and that's really what we were trying to show. Let me finish that up here, and I'm sorry for being a little bit messy on this. We were trying to show that 1 and 2 together, well, that's the angle AOB. Angle AOB is equal to 2 multiplied by 4 and 5 together is the size of the 4 and that should have been twice 3. Now 3 and 5, remember, are the same size, so it's okay for that to be a 3 and that to be a 3. Just for the diagram, it's this one was 3 up here. So that's twice 3 and 4 together, which is twice the angle ACB. Okay, so there's our conclusion, and that's theorem 19.